data center Tetris. So we're going to look at the utilization of space and power only, just to make things build up in complexity. We're going to ignore cooling for a moment. And let's play that game of Tetris. So using the design assumptions for IT equipment on the left, it's very easy to use all of the capacity available because of the nature of the IT equipment that we're installing. But in reality, things are different. And the units come in different sizes, they're decommissioned and removed. And very quickly, in the real data center, we reach a point where we need to install this particular unit. And there's power over in this cabinet, but no space. There's space in this cabinet, but no power. So we're essentially stranded with respect to that unit. But on the left, because everything was predetermined from the beginning, we used all of the capacity. So what can we do? Well, if we're using a DCIM tool, we'll know pretty closely in real time where space and power are distributed in the room, where they're available. And so we could plan for, say, moving some power from this cabinet over to this cabinet to free up capacity and allow us to continue. So that's how defragmentation, so to speak, of capacity is done on space and power. But space and power are very intangible. You can track them if you're very careful and accurate. You can track them definitively over time. But cooling is a whole other issue. So, like I said, space and power can be tracked, but cooling is a bit more difficult. It's done by air, mainly today, and it's invisible. So, and IT equipment needs cooling just like it needs space and power in order to operate. So that complicates things a lot in this game of data center Tetris. So here is just a quick illustration of fragmented cooling now in the data center. Now, you can't see this in your real data centers because air is invisible, but with simulation techniques, the air does become visible. You can see it. So here's how cooling becomes fragmented. So we have a data center, one that is loaded to 60% using the design assumptions for the IT equipment. And the other one is the same data center, same load, 60% load, but more realistic cabinets, IT equipment, and so forth. So let's hide the cabinets. So we'll hide the cabinets so we can see the cooling distribution. And then make the cooling visible. And hopefully you can see that on the left, all of the air, which is the cooling, is colored blue. That means that it's actually being used by IT equipment. And there's very little fragmentation of the cooling. On the right, there's a lot of these gray streamlines. That means that the air is bypassing the IT equipment. And it's fragmented. It's not being used. And that effect, just like fragmentation of power or space, will result in lost capacity. And just a comment about how people are trying to deal with this. Again, the techniques have not been available to deal with this very well until now. But one way that people have been trying to deal with it is by temperature monitoring in the data center. And then trending the temperature to try to predict when the cooling will fragment to the point where you can't load a unit. But trending doesn't work for predicting the weather, as we'll see in this example. So here's a weather trend from Sunday through Thursday that says that the temperature on Friday will be 48 degrees. But the temperature, just like it today, dropped tremendously from yesterday. So trending doesn't work for predicting the weather. The only way to predict temperature from day to day is to model the weather, all the airflow patterns, the pressure distribution across the various zones and so forth. That's how you predict temperature for weather. And the same applies to the data center. So here's a quick example. We are going to load up 5 cabinets in a fairly normal sequence of loading. different types of IT equipment are coming in. And as we load, we are looking for space, power, and low temperatures in order to find safe places to load across these cabinets. And we're tracking power utilization as we go. So we've already used up all of the power in the center cabinet because we have a blade computer in there. So the rest of that space is unusable unless somehow we redistribute power to match it. We've reached a point in the sequence of loading where we have hot temperatures at the top of this cabinet. And so that means that's off limits now for loading. So we've fragmented probably a bit of power and space because of temperature. So we have a hotspot there, but we don't know why. All we know is, it's a hotspot. Just like when you feel sick and you take your temperature, and if you show a fever, you don't know why you have a fever. You just know you're sick. So let's keep going until we reach a point where we need to load this 4U server, and we see 1, 2, 3, 4 safe locations to load. And we install that unit, and now the alarms go off. So this happens on occasion, which is a disaster, of course. And there was nothing about of that sensor on the front of the cabinet. It didn't even change before and after loading, because all the problem was on the inside of the cabinet. And so this is common. This is what we see all the time. When clients call us in, they say, my monitoring system is not showing the problem that I feel. And you can't see air, so they don't know why. So we end up building a model and showing them things like this. And about half of all cooling-related capacity problems are due to inside cabinet problems. So blanking, containment, none of that helps. See the containment gentleman stepped out of the room, so I can't discuss this with him right now. Maybe after the presentation. Anyway, just to sum up, these are just a partial list of things of changes in your data center that cannot be predicted during the design of the data center that will happen. And when these happen, capacity fragments. There's no getting around it. So the only question is, can you predict ahead of time if one or more of these are happening, what is the impact on capacity? And given the fact that if you're able to predict it, maybe you can work out a solution before you actually install and build that problem into your data center. That's the goal. And just one comment about, so this problem is huge, as we saw from a financial standpoint, and a career standpoint, and everything. So we believe it is driving the popularity of DCIM tools. But as we discussed, DCIM tools, they track IT assets, space, and power. So they don't track cooling. So they cannot help with this capacity issue. They can help with the asset tracking issue and the power tracking issue, but not the capacity. The only way to do capacity is to have those things, plus being able to track cooling, and how they all relate to each other in real time over the lifespan of the data center. So what is the answer to capacity assurance then? And that's where we get to this concept of predictive Eason, where you can see all of that in one view, but also be able to simulate or predict cause and effect before you actually make those changes in the data center. So this is a typical predictive DCIM database, so to speak. It has a complete IT asset list. It also represents the data center in its 3D configuration. Power distribution is in there and connected to a live monitoring feed for power consumption. So you know, so this model knows at any point in time how much power is being consumed and how it's distributed in the room. And of course, the simulation capabilities for cooling as well. All that in one model and with the simulation capability built in. So this is the basis for predictive Eason. It's this 3D mathematical representation of the data center itself. So we're not separating out IT and managing that on its own. We're not doing the cooling on its own. It's the integrated system that is being tracked and managed here. So that is the basis, we believe, of predictive Eason, of managing capacity proactively in the data center. And so this model is only as good as the data that is feeding the model. And so that's where the DCIM functionality comes in. So in this setting, the DCIM functionality for managing the assets, for managing power utilization and so forth, is the input to this model. So above the line, you can think of as the DCIM, traditional DCIM functionality, feeding into what's below the line, which is the model, or which is used to make the operational decisions. So let's rewind the clock on that data center where we lost about 30% of its loading potential, its capacity, and use predictive Eason to see how it would change things. So here is the data center on day one. Now we have a model of the data center now. We might have even received it from our mechanical design firm that designed the data center originally. And now we can use the model to load up the representations of the cabinets that we purchased, the IT equipment that we purchased, and also any new plans, IT deployment plans that are coming maybe in the short term, the next few months, and then also all the way out to end of life. So we're putting this data center on a timeline, and on day one we may have only installed just a few units of equipment, but if we project out to the future, all the way to end of life from this point, we've already lost a lot of capacity. And again, that came from that list of changes that will always occur in the data center. That's what caused that capacity loss. So now what we can do is use the model to understand why all these red U slots, which represents lost capacity, why they're there. And they can be there because of fragmented space, power, or cooling. We're just going to stick with cooling as examples here because it's the most complicated problem, given that, again, cooling is invisible and so forth. But here's an example. If we zoom into the networking cabinets, the cabinets we bought and how they're stacked up together cause hot air from one unit to feed the next unit. And this is a very classic example of fragmented cooling. And so what we can do before we actually install the equipment and get it up and running is we can maybe modify the cabinets a bit to make sure the air doesn't mix like that. So here is one example of doing that, a zoom in of that. And when we apply that change, you can see how much better the cooling distribution is. Alternate plan that results in much less lost capacity compared to before. So we're solving problems that are going to happen today, which is, again, much cheaper and less risky. Now, this data center will continue to evolve, and at a future point in time, now we're coming in with a whole new set of equipment, again, that wasn't anticipated. It was going to look like this. And so that change results in a lot of lost capacity down the road. And we can, again, use the model to understand why. So here is there's a lot of, there's not much air being delivered. There's hot spots at the top of these cabinets. And one option would be maybe this whole cluster of equipment, which has to go together, could be put in a different part of the data center. So we're going to simulate moving it to the center. So here's the original plan, which had hotspots. Here is a different plan, an alternate plan. And it is a little difficult to see, but there's less hotspots. Can't get rid of all hotspots. No data center is ideal. But if you see how much blue there is on the front of the cabinet after relative to before, you can imagine imagine the improvement. So again, here's another example of, now we're down the road and we're doing the predictions, and we are avoiding, with an alternate layout, loss capacity. So that's the idea. And if that process is continuous, you can mitigate this problem. There's no way of completely getting rid of that problem, because no data center, again, is ideal, but you can mitigate it. And that, going from 30 to 12%, represents millions of dollars in capacity that would save. Sherman and so forth. It's called the ACE Data Center Performance Metrics. And so the centerpiece is actually the capacity. That's what you want out of your room. You want to know that you're not going to be stranded at any point in time. But you also need to have that capacity at a certain level of availability. You can't risk your servers either. And you can't do it at an infinite cost. It has to be cost managed. So these three together form the highest level, most complete set of metrics for managing the physical data center. And what we have found in working with clients is that the game, this data center Tetris game, is really balancing the ups and downs of these three metrics. You can always overspend and solve your capacity problems, but you don't want to do that. Or if you go after your efficiency problem,